Hello, welcome to Chemistry 101 tutorials. If it's your first time joining us, please go down there and hit that red subscribe button. Okay, today I have one question regarding mechanisms, that's hydrohalogenation of alkene. Alright, before we can proceed to answer this question, let me first remind you about certain things that will help you to answer this question. Alright, so I'll divide this. So remind you about nucleophile and electrophiles. Okay, electrophile. Alright, so a nucleophile by definition is an electron donor. An electrophile is an electron acceptor. Okay, so you normally recognize nucleophiles by negative charge. So for example, cyanide, and electrophiles by positive charge. For example, proton, sodium, whatever is positively charged. And sometimes nucleophiles have got lone pairs of electrons. So, for example, so let's say this is carbon. R in this case represent a methyl group. Okay. So here in this case, the lone pairs of electrons will act as a nucleophile. Alright. So sometimes you can have similar functional group with nucleophile and electrophile at the same time. So in this case, if you look at this, you will see that the oxygen is directly bonded to carbon, and because of the difference in the electronegativity, the oxygen has got higher electronegativity compared to carbon, and as a result it will withdraw or polarize these electrons towards itself, hence rendering it to be partially negative and the carbon be partially positive. So the partial positive or delta positive carbon will act as an electrophile in this case. You can also see the nucleophiles by double bonds and also by triple bonds. Okay, so in this case I will just put something like that. So these triple bonds and double bond, they have higher electron density. Okay, so they act as a nucleophile. And one other important thing to know is that the nucleophile, say like so, the arrow move from the nucleophile to the electrophile. For example, in this say proton, we'll have the arrow moving, attacking the hydrogen there and then forming HCN. Alright, so nucleophile attacks the electrophile. So here you can see that we put a full arrow just because this represents a lone pair of electron. So if it was one pair of electron in the example of radical mechanism, so for example we have this kind of a bond and we irradiate this maybe with ultraviolet radiation, and the bond will split according to this way. So we will have one curved arrow and another arrow there. This is not a full arrow, so this maybe you can't see it clearly, but it's not a full arrow, it's a half arrow. It's like this. Okay, it's not a full arrow like this one. Full arrow represent a lone pair of electron, and this is one electron. So in this case you will form two radicals. Alright, And okay, so now that you know how to differentiate between nucleophile and electrophile, let's answer the question. The question requires you to provide a markovnikov product. So now first again let's define what markovnikov product is. So markovnikov product from this question is that product of the product which will form as a result of bromine substituting to the highly substituted carbon. So this carbon is highly substituted because it's bonded directly to 1 carbon, 2 and 3 carbon. And here between this double bond, this carbon is only bonded to 1 carbon. Hence, it will form anti-markovnikov if the bromine goes and substitute on this carbon. Alright? So that means here in this case for markovnikov product, we have to make sure that the bromine is on this carbon. So this is because the markovnikov product is the most highly stable product. Why? Because normally the carbocation will mostly prefer to form on the carbon which is highly substituted, because then the positive charge will be stabilized by electron density from the methyl groups, unlike when it's only bonded to 1. So it will be less stable. So let's see how. In this case, we will provide a mechanism. So I'll write it again, HBr. So then the lone pair of electron will act as a nucleophile and will attack here the hydrogen proton. So here there is a bond. So when the double bond attack this hydrogen here, the bond between hydrogen bromine will break and all the electrons will go to bromine. So in this case you will have a positive charge will form there because it's markovnikov product CH3. Alright, so if your carbocation, for example, formed here, so that will be anti-markovnikov. Alright, so in this case you will have bromine be negative charge because the electron went all to bromine. So now this will act as a nucleophile. It will attack the electrophile, okay, the positively charged carbon. So you will have a situation like this, and your product will be markovnikov product, Br CH3. Okay, I hope you understand that. So if the Br was on this carbon, it was gonna be anti-markovnikov. So the Br or the halogen is now on the highly substituted carbon, which is the markovnikov product. So I will try to explain this again further. So for example, let's consider this. It's a methyl group. It's a primary carbocation, hydrogen there, and secondary because it's bonded to 2 methyl groups. Tertiary because it's bonded to 3 methyl groups. So the cation stability will be like this. So from here to here, this will be the increasing stability. So that means the most highly stable is this one, which is substituted to 3 methyl groups. This is because in this case, these R groups will be the electrons will be the electron density from this group will be stabilizing this positive charge. Okay, so unlike when you have this kind of situation here, this will be very less stable because you have only hydrogens which are not having high electron density like here. So if you enjoyed this video, please put a thumbs up, and let's meet in the next one.